Okay, hello class, my name is Ainala and I'm graduated Bachelor Computer Engineering student, and for now I'm your TA in Deep Learning course, which is 10 in 441 semester. As you know, TIC classes topic divided in two categories, and the first one is practical and implementation, which you learn how to coding with Python language and using some frameworks such as Transformers, PyTorch, NumPy, Pandas, and Cban. And the second category which you must to learn at is the theoretical of the course, and you must learn how to solve the problem in theoretical, and which is my duty to learn you in this session with a theoretical version of that. Okay. At the first, we just tell you some theoretical and historical something of neural networks in deep learning, and for that, I just say something, and after that, we just solve some examples to learn more about that. In deep learning refers to training neural networks, sometimes very large neural networks using in some cases. And the first one we want to show you one example using housing price prediction. Let's say we have a data set with some houses, and you know the size of the house in, I don't know, square feet or square meters, and you know the price of the house, and you want to fit a function to predict the price of the house as a function of its size. So if I want to write it, it's we have two dominations. The y1 is the price of the house, and the second one is the size of the house. The price of the house, like we have, I don't know, $10 not makes sense, but like $1,000, 2,000s, let's go on, like I don't know, $1,000,000. And the size of the house is like square by feet or square of the meter. You can say, I don't know, 18 square of the meter, 19, 100, 150, and 200, and goes on. So each house has size of the house, and each of them has price. As you know, when we increase the size of the house, the price of them must increase it too. So imagine that we have some houses in here, 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 and here. The X domination tells us the size of the house, and the Y domination tells us the price of it. And if you're familiar with linear regressions, you might say, well, let's say put a straight line of a data like that. Let me show you with the red line. So we get say a straight line like that, but to be put fancier, you might say, well, we know that prices can be never be negative. Why? Because if you imagine that, we can say the price of the size of the house can be negative. It must be positive. And although you want to say, if we had this straight line as our prediction for the size of the house by the price, we can say like that, this means the destination of the size of the house by the price. And we want to predict at first some linear regressions like this line. We say, okay, if in this point we have this size of the house, the price must be that. Do you understand that? Alright. So we want to predict a line. We want to predict the price of the house by we have the given of the size of the house. So at the first we say we use a straight line to predict them. We saw some houses data. In here we have eight of them, and we want to predict the most common for that. They have so many issues with that. Uh, like when you imagine that, at first I said it can be a negative. So instead of a straight line fits, which eventually will become negative, let's bend this curve here. So this thick red line ends up being your function for predicting the price of the house as a function of its size, where it's 0 here and in this part I mean. And then there is a straight line fit to the right. So you can think of this function that you have just fit to housing prices as a very simple neural network. It almost simplest possible neural network. Let me draw it here for you. We have as an input the neural network of the size of the house, which we call x, and it goes into this node, this little circle, and then its output the price, which we called it the y1. So this little circle, which is a single neuron in a neural network, implement this function that we draw on the left, and all that the neurons does, it inputs the size, computes this linear function, takes a max of 0, and then outputs the estimated of the price. So if we got that, I don't know, integer or so like double numbers, we got that size, and we take that to this machine, and this calculated, and after that we call it that calculated like function, and we use some methods and some activation function, I don't know, like sigmoid, like relu, and something else, and after that the output must be a price. And by the way, in neural networks literature you will see this function a lot, this function which goes to 0 sometimes and then it takes off as a straight line. And this function like that, as you see, we say, I don't know, after 19 square per meter, we just said it has a value on this size of house by this price. But if it's less than that, we can say that, sorry, I must answer one. So we continue that. Dr. Dodo did just send me a message. She thought I'm not in class. She think I must send another link. Okay, let's back. We just say this function is called relu, like this one, this red one. Just I draw it. This function is called a relu function, which stands for justified linear and units. So that's called relu. And justify just means taking a max of 0, which is why you get a function shape like this. And you don't need to worry about relu units for now, but it's just something you will see again later in course. So if this is a single neural network, really a tiny little neural network, a large neural network is then formed by taking many of the single neurons and stacking them together. So if you think of this neuron that's being like a single Lego brick, you then get a bigger neural network by stacking together many of these Lego bricks. Let's see an example, and let's say instead of the predict the price of house just from the size, you now have other features, not just for the size of the house. We just predict the prices of them. So for this project, we just think, not project, this scenario, housing price prediction. You know other things about the house, such as the number of bedrooms. We could write as I don't know, what's in number of the bedrooms as a feature on the inputs, such as the last one we use size of the house. This is what we want to predict that, and size of the house. And you might think that one of the things that really affect the price or the, I don't know, to number of the families, and it's really based on the size of the square feet or square meters, and the number of bedrooms that determines whether or not house can fit your family's size. And which one we can say? Oh, zip code. Zip code maybe as feature tells you wakeability. So I don't know, it's neighborhood highly wakeable thing just works to grocery store or something else. And we can say so for all of them, and something else we can use such as wealth. Each of them is you look at them like a feature, like input. We get some that's input and take them into some function or some program, and we want to just predict some prices. And so that's based on the size and the number of bedrooms. You can estimate the family size, their zip code based valuability, and based on zip code and wealth can estimate, I don't know, school quality or something like that. And then finally you might think that well, the way people decided how much they're willing to pay off the house, I know, it's they look at the things that really matter to them. And we want to know how I manage neural network is that when I implement it, I needed to give it just the input x and the output y for the number of examples in your training sets, and all these things in the middle they will. Like we use these tools, we want to create a feature like as I told you to you, family size, and I don't know, zip code. We can understand some feature like vocabulary, and I don't know, zip code and wealth, like school quality. And these two we can understand one feature like I don't know, something, and we can use some functions such as the ReLU or sigmoid. For here we use ReLU. Although all of these neurons that are circle using a ReLU function, it's not necessary, but for simplest thing we think all of them are ReLU in this function. And after that we just know some price which we call y, and all of these one number of the bedroom size, zip code, wealth, we call our inputs, they called x. And although we can say their input layer, their output layer, and all of these neurons in the middle we can say it hidden layer. So, oh my god. Pardon me. Oh shit. I'm so sorry. So, for house price prediction, so we actually implement this, where here you have a neural network with 4 inputs. So the input feature might be the size, number of bedrooms, and zip code. I don't know, postal code and wealth of the neighbor. And so given these input features, the job of the neural network will be predict the price which we called y. And notice also that each of these circles, these are called hidden units in the neural network, that each of them takes its input all for input features. So for example, rather than saying this first node like that, represent, I don't know, family size, or we can say family size depends on feature 1 and feature 2, or x1 or x2. Instead we're going to say neural network, you decided whether you want this node to be, and we'll give you all 4 input features to compute whatever you want to see. So we say that layer that this is input, which like number of the bedroom, size, zip code, wealth, is input layer, and this layer, the middle of the neural network, are densely what does it mean is densely? It's like a connected graph, which we just imagine that if all of them is one node, all of these nodes must have an edge with the second node in the second layer. That's called them dense. And it must be densely connected because every input feature is connected to every one of these circle in the middle. And the remarkable thing about neural network is that given enough data about x and the answer, which is y, given enough training example with both x and y, neural networks are remarkable good at figuring out function that actually map from like x to y. So we have some inputs in x and we just predict something in y. And in basic neural network, it turns out that has built out your own neural network, you'll probably find them to be most useful, most powerful in supervised learning, and meaning that you are trying to make an input x and map it to some output y, like just saw in house pricing prediction example. Like we said in the first one, we just imagine that we have one input and its size of the house, and we just predict the price one, and we saw it as a two domination. And in the second one, if we imagine that we have 4 input, we can think that it's 5 dominations, which is 4 of them is the input, and the last domination is the output one. So the neural network representation, we can say, start with focusing of the case of the neural networks with what was called a single hidden layer. And let me draw it for you. x1, let me come here, x1, x2 and x3, and there's some neurons, and because it's densely, we must draw an edge between all of the first layer to the second layer. Here's a picture of the neural network. Let's give it different parts of this picture some names. We have input features, we call them x1, x2 and x3, that stack up vertically, and this is called the input layer of the neural networks. So maybe not surprisingly, this contains the input to the neural network, but there's another layer of the circle, and this is called the hidden layer. I draw it with yellow parts. Then there's another layer of the circle, and this is called hidden layer. Do you have any idea why we call them hidden layer? Why we didn't call anything else, or why we use that name for them? Okay, I come back in a second to say what the word hidden means, but before that, I just want to tell you uh, the final layer, which is the answer, and we show them as the y hat. In this case, just one node, and this single node layer is called output layer, and is responsible for generation the predicted value y hat. In neural network that you train with supervised learning, the training set contains the value of the input x as well as the target output y. So the term hidden layer refers to the fact that in a training set, the true value for these nodes in middle are not observed, and we can't see them. That is, you don't see what you should be in the training set. You see what the inputs are, you see what the outputs should be, and but the things in a hidden layer are not seen in a training set. So that kind of explains the name hidden layer. Just because you don't see its training set, let's introduce a bit more notation about that. Whereas previously we were using a vector x to denote the input features and alternative notation for the value of the input features. Yes, Mr. I can see all your name. Ibrahim Hussein.
Haidar Ibrahim. Hi, sir. Good morning.
Good morning to you.
I have to ask you, how do we decide how many hidden layers in neural network should we have?
It's a perfect question. It's a perfect one. Thank you for asking that. Look, we always have just one input layer. It can be a numeric of inputs. It might be 10, 3, 5. It doesn't matter. But in hidden layer, it's not necessary. We just have the one hidden layer like that. We can use another hidden layer for that, and another hidden layer, another for that, and the last one it's must output layer. In addition, I can say output layer neurons. It's not necessary to be one. It can be I don't know, 4, 5, and something else. But the question is make that why we just have so many hidden layers, why we just don't use it with one, because of the complexity of that. In some cases we can't use with one layer, one hidden layer in problems, because the problem is so difficult, and in one hidden layer we can just create some features to answer that with that input. So we can have many hidden layer, and it's became with that difficulty. In a moment I just give you example. You can see we the simple question with AND gate and OR gate. If you don't know what's AND and OR, just imagine that we have two input x1 and x2, which the domains of that are 0 and 1, and imagine that truth table. There are just four cases for that, and if x1 is 0, x2 is 0, x1 is 0, x2 is 1, and x1 is 1, x2 is 0, and x1 is 1, x2 is 1, the answer of the AND gate must be that. Okay. We can say in AND gate, just if both of the not both, all of the inputs are 1, we can say the answer is 1. Either one, we say the answer is 0. And the O gate is x, we can use x1, x2. All of the case must be 0, 0, 0, 1, 1, 0, and 1, 1. The answer of that is the result. the answer of the OR gate. So 0 0 is 0 and 0 1 is 1, 1 0 is 1, 1 1 is 1, and we can say if just one of the inputs are 1 and not false, we can say the answer is 1. And if I want to draw the neural networks for them, as you see, we can use one hidden layer. I show you in the continuous of this session. But if we want to answer XOR gate, XOR gate is like that. If x1 is 0 0 0 1 1 0 and 1 1, in this case, let me show you the image of them. We don't have it. Okay, this is not. I show you like that. If the number of inputs, which there are 1, is odd, what does it mean is odd? It's like 1 is odd, 2 is even, 3 is odd. I'm sorry, I'm writing in Persian. 1 is odd, 2 is even, 3 is odd, 4 is even, 5 is odd, and something like that. I mean, modulated by 2. If they're odd, the XOR gate must be 1. The other one, if the number ones in input is even, there are 2 number 1, which is even, the XOR gate must be 0. So in this case, we can handle it with one hidden layer. We must use 2 hidden layer. So for your question, you said we can't use multiple hidden layer. Your answer is yes. It depends on the question what they want to use. Is that clear, Mr.?
Yes, sure, it's very clear. But I have another question.
Yes. You can ask, please.
So, what happens if we add too many hidden layers? So, and how does the number of neurons of each hidden layer affect performance? As you know, we have infinity added. So if I have very performance GPU,
Yes, yes.
and you got that?
Yeah. You mean why we just don't use so many hidden layers? If we can't use so many hidden layers, what's it necessary? Yes.
Yes.
What you say? If the hidden layers are so much, the computation makes so difficult. We want to figure it out how many hidden layers that make the answer is always not by always by the threshold it may be correct, and but if we create some hidden layers that's not necessary, the computation it's making me so complex. For some, I don't know, some PCs, some GPUs that you run your code, because for each layer it doesn't matter its input, its hidden layer, or its output. Between each layer, the neurons are densely connected with the last layer. So the shape of the neural network is like that. So you can say, I will say it at the moment, but you must say what's these edges. Let's call them edge. The line between two neurons of the different layers. All of them is one simple computation. It's like sum and multiply. But if our hidden layer are so too much, we have so many computation for calculating. So for each, imagine that we have, I don't know, 100 neurons here and 200 neurons here. The number of edge is 100 multiplied by 200. But if we imagine we have another hidden layer like even 50. The
Excuse me, I hate to interrupt you, but
yes.
how does the number of neurons in each hidden layer affect performance?
uh, Effect for what? You know, because hidden layers number is not the same. In here we can have 100, in here we can 200, it here we can, I don't know, 50. It's not necessary, and it's not necessary to be a same.
Now we gather reach to our question. Why do we use activation function in hidden layer and not just in the output layer? This is
No,
my
we
general
use
question.
activation function for them. No. We use all of them. No, look at that. For each edge, you see that. I will tell you in times. You can be patient, but I told you. Okay. Um, Imagine that there's some inputs, and each edge is, I don't know. That's inputs multiply, oh my god, multiply by some weights. I told you, I will told you what's the weights, and after that we use all of them for activate. They they get partial sum of all of the last layer nodes, like that, x1 w1. Guys, I'm sorry, sometimes I write numbers in Persian. uh, I will pay attention for that. Like, I don't know, x2 w2 plus x3 w3, blah blah blah, x n wn. After sum of all of them, imagine that there's sum or a. We get all of the a to that activation function a. It can be ReLU, sigmoid, or something else. But pay attention for that. We use all these activation function for all these neurons, not just for the output layer. For all neuron that have the second, have the last layer of that, and they calculated this I don't know, combination of sums and multiply. We use function activation function for that. So it's not for just the output one. Did I answer your
Yes, thank
question?
you. I get that.
Yeah, you're welcome.
Thank you. Thank you for your time.
You're welcome. Okay, let's back to this neural network. In a neural network that you train with supervised learning, the training set contains a value of the input x as well as the target output y. So the term hidden layer refers to the fact that in the training set, the true value for these nodes in the middle are not observed. That is, you don't see what you should be training set, or you see what the inputs are or what's the outputs are, and but the things in the hidden layer are not seen in this training set. So that kind of explain why they call them hidden layer, just because you don't see it in the training set. Let's introduce a bit more notation. We were using a vector x that's our input layers, and will be a subscript a square bracket 0, and term a also stands for activation, and it refers to the values that different layers of the neural network are passing on the subsequent layer, like that. Let me draw it for you. Your inputs x1, x2, and x3 imagine that we just have 3 input neurons, and the first hidden layer are them, and they're fully connected, they're dense like that. Their input layer, their hidden layer, and for the simplicity, just imagine we just have one hidden layer, and this is the output layer. And okay, and activation of the input layer A superscript 0, we call them. All these inputs they call X, because of the number of layers we call A superscript 0. The next layer, the hidden layer, will in turn generate some set of activation, which I'm going to write as a script superscript square bracket 1, because it's the second layer, but we use them 0 base. Yes? Anyone has a question? Okay, let's continue that. So in particular, this first unit of the first node, we generate a value A superscript bracket 1 script 1 and A1 1 A2 2 superscript 1 AN superscript 1. The superscript means the number of layer which it tends in, because if it's 0 base and the 0 is input and the hidden layers starts with the number 1, and in the other case the number of that is the number of neuron in this layer is 1 2 3 4 until the end. Now we have a superscript 2 and so on. That means each a layer after that we have. And so a superscript a square bracket 1, and this is 4-dimensional vector you want in Python, because the 4 multiply 1 matrix, or it became a 4-column vector like that. It's A1 superscript 1, and this means them. They have A1 1, A2 1, A3 A3 1, and for this case just imagine that there are 4 neurons, A4 1, and it became a 4-dimensional vector because it's 4 multiply 1 matrix, or 4-column vector, which units or 4 hidden units in this hidden layer. And then finally the last layer, some value of A2, which is this, just a real number. It's not so many neurons, just one number. And so y hat is going to take on the value of A superscript 2 in this case, not all of the cases, because in here we just have one hidden layer. So this is to how to, in logistic regression, we have y hat equals and it logistic regression, which we only had one output layer, so we don't use the superscript brackets. But with our neural network, we're now going to use the superscript square brackets to explicitly indicate which layer it came from. And in funny thing about notational conversation in neural network is that the network that you've seen there is called a two-layer neural network. It means if you want to say how many layer it's called, you can use that a hidden layer plus one, and that plus one is the output layer. And we can say the layer is not in the number of layer, like we say if our neural network is 4 layer, that means this is input, this is input, this is hidden layer 1, this is hidden layer 2, this is hidden layer 3, and this is output layer. And when we call I have a neural network with 4 number of layers, that means I have with 3 hidden layer and 1 output. Why we call it's 4? Because we have 3 hidden layer and overall we have 5 layers. Why we called it 4? Because of the number of the edge layer. This is 1, this is 2, this is 3, and this is the 4. Because of that we call them a neural network with 4 layers. And we don't count the input layers, so the hidden layer is layer 1 and the output layer is layer 2 in our example. In our notational conversation, we're calling input layer 0. So technically maybe there are 3 layers in this neural network, because there's the input layer, the hidden layer, and the output layer. But in conventional usage, if you read research papers and if you show some courses, you see people refer to a particular neural network as a 2-layer neural network, because we don't count the input layer as an official layer. So something that we'll get to later is that the hidden layer and the output layers will have parameter associated with them. So the hidden layer will have associated with its parameters, we call them W, it's aka for weight, and B, and it stands for bias. And I'm going to write superscript squares 1 to indicate that these are parameters associated with layer 1 with hidden layer, and we will see later that W will be 4 by 3. Let me write it for you, like WB and superscript 1, and it's like for 3 matrices, and this is B4 on 1, because for each layer we just multiply each weight for each input, and last we just add 1 bias for that. For like this example, just imagine we have 3 inputs, which is x1, x2, x3, and the second layer, which is our first hidden layer, is with 4 neuron. I'm sorry, I rated Persian. With 4 hidden layer neurons, and I said it's dense, fully connected. So for for the first neuron of the hidden layer 1, it's calculated like that. The weight of this neuron that in graph, which one node is h1 and the second node is x1, we called it w1 superscript 1. This is w2 superscript 1. So for calculating h1 is x1 multiplied w1 superscript 1 plus x2 w2 superscript 1 plus x3 multiply w3 superscript 1 plus, yeah, it's over, plus 1 bias for that, we're calling 1b. So for each one, if in this case, if we have, where do I write it? Oh yeah, W's are, there will be 4 by 3 matrix, and the bias one be a 4 by 1 vector in this example, where the first coordinate for comes from the fact that we have a 4 nodes uh, for nodes of our hidden units and layer, and 3 comes from the fact that we have a 3 inputs. Features we talk later about the dimensions of these matrices, and it might make more sense at a time, but in some of the output layers has associated with it also parameter. And W superscript square bracket 2 and B superscript square square bracket 2, like that, is for the next layer. And it turns out the dimension of these are y1 by 4 and y by 1, because we just have one output, one neuron in our output layer. So in this case, opposite of the last layer, our W superscript 2, that mean, and B superscript 2, the size is 1 by 4 and y 1 by 1. So we will go over the dimension of these matrices and vectors in I don't know, next example. So you've just seen what a 2-layer neural network looks like. This is a neural network with one hidden layer. In the next example, we go deeper in exactly what this neural network is computing. Alright, so in this example, a logistic regression, but it's repeated a lot of times. Let's take a look. So this is how a 2-layer neural network looks. Let's go more deeply into exactly with this neural networks computes. Now we've said before the logistic regression, the circle in logistic regression really represent 2 steps of computation rows. So if we want to show you a neural network in a representation, just imagine that these are our inputs. Sorry. Okay, these are our inputs, x1, x2, and x3, and we have a function here, and the output of this function is our answer, which is y hat. You computed these function. Let me write, and after that I explained it to you. WT, that means transpose, multiply x plus it's so let me write bigger. It's a neuron, it's one single neuron, and so it's W weight, it means transpose by x plus B we're calling Z, and after that we use activation function for Z, and we're calling alpha for that, and the answer, which is alpha, is that y hat. So you compute Z as follows, and second you compute the activation as a sigmoid function in this sample of Z. So a neural network just does this a lot more times. Let's start by focusing on just one of the nodes in a hidden layer. The first node in the hidden layer, so we use out of the other nodes for now. And for similar to logistic regression, on the left, this node is the hidden layer. There's two steps of computation. The first step, think of as the left half of this node. It became compute Z equals W transpose X. X means input and W is our weights, and plus B. What's B mean? It means bias. And the notation we'll use is these are all questions associated with the first hidden layer. So why we have a bunch of square bracket there? Let me write it for you. Just imagine that and don't forget it. And for more detail, I write them in here. x1, x2, x3. I just show you step by step for all calculation of them. We have this for first neuron of the first hidden layer, and Z1 superscript 1 become W1 X is transpose and became 1 plus B1 A1 1 is the activation function of Z1 1. So for generally we can say A1 script 1 we call J. Its layer, its node in layer, and like for the next one I write them Z2 superscript 1 W2 transpose 1, and it's multiplied by X plus B2. I'm sorry, I just write them in Persian. Guys, for many cases you just want to define or map them because sometimes I forget it. These are Persian numbers. This is 1, this is 2, and this is 3. If I forget to write them, tell it to me, and just remember these are in Persian, these are in English. Sometimes I forget to write them in English case. So B2 superscript 1, and this is Z function, and after the activation function it's became to that superscript 1. So let me explain it to you. The first step, and think of as the left half of this node, it computes Z equals W transpose X plus B, its bias, and notation will uses there are all them for each layer to first hidden layer. So that's why we have bunch of square bracket there. This is the first node in hidden layer, so that's why we have the subscript 1 over there. So first it's does that and so sorry in the second step is compute A11, I mean these. it's the sigmoid, or the answer of the activation function of the z1. The z1 was the weight. It's here in, I don't know, in it's w1, it's w2, it's w3, and the x's are our inputs. And for each neuron we have just one bias. Don't remember, we don't have for each edge we have one bias. For all of this edge we just have, for this neuron we just have one bias. And after that we have z, and the a computes equals to sigmoid of z, like this. And so for both z and a, the national convention is that a, and we can say letter and I for that. I just here is j, not l. And here's a superscript. A script bracket refers to a layer number, and subscript here refers to the nodes in the layer. So the node will be looking at the layer 1, that is hidden layer node 1, and so that's why the superscript and subscript were both 1 and 1 in here. So that little circle, that first node in the neural network, represent carrying out these two steps of computation. Now let's look at the second node. Let me draw it for you. No, I drew it. In this black one, similar to a logistic regression units on the left, this little circle represents two steps of computing. The first step is compute z. This 2 equals sigmoid z. 1 in superscript and 2 in subscript. Yes. Again, feel free to reuse that, but you can use subscript and superscript notation inconsistent with what we have written here above. In this place it's a little dirty. So with in the first two hidden units in a neural network, having units 3 and 4 also represents some computation, like the first one and the second one that I showed to you. So now let me take this pair of equations, and this pair of equations, let's show them in here. So here are neural networks, where I just use them. If you go through and write out corresponding equation for the third and fourth hidden layer, if we imagine we have them, units, you got the following. So let me show the notation is clear. This is the vector weights 1 1. This is a vector transpose times x, so that's what's a superscript t, that means transpose. The represented, it's a vector transpose, and as you might have a guess, if you're actually implementing a neural network, doing this with in Python, we can use not necessarily for Python, we can use so many languages, but for common ideas we just use it with Python. We can use with a for loop. Seems really inefficient, so we use some frameworks, and what we're going to do is take these equations and vectorize. So we're going to start by showing how to compute z as a vector. It turns out you could do it as follows. Let me take these w and stack them into matrices, and then you have w1 1 transpose it. Let me write it for you. w1 1 transpose. So let me write it. Z11 is 1 transpose x plus B11, and A11 is the sigmoid of Z11. Z21 is W21 transpose x plus base 21, and A21 is sigmoid of Z21, and Z31 is W31 transpose x plus base 31, and A31 is the activation function Z31, and this Z41 is W41 transpose x plus B41, and the A41 is the activation function of that. So okay, so for W11,
Yes, it's okay.
yes, do you have any question?
No, I just tell you it's okay.
Oh, thank you. Yes, and like imagine for this one, we have W11 transpose, so that's a row vector, or this column vector transpose give you a row vector. Then W12 transpose W12 transpose W13, and then transpose W14, and so go on. So by stacking those for W vector together, you end up with a matrices. And another way to think of this is that we have a 4 logistic regression units. We can say each of the logistic regression units has a corresponding parameter vector, and W stacking those 4 vectors together, and you end up with these 3 matrices. So if you then take these matrices and multiply it by your input feature like x1, x2, and x3, you end up with how matrices multiplication works. And you end up with W11 transpose x, W21 transpose x. After transpose x, it's multiply, but for make it easier, I just don't say the multiply. And W41 transpose x, and then let's not figure it the biases. So we now add these a vector b, b11, b12, b13, b14. So this is basically, this then is b superscript 1 subscript 1, and b superscript 1 b superscript 1 subscript 2, b superscript 1 subscript 3, and these are 4 rows. Each of these 4 equations that we had above. So in other words, we've just shown that these things is therefore equal to z11, z12, z13, z14, and as defined here, maybe not surprisingly, we're going to call this whole thing the vector z1, which is taken by stacking up these individual of z's into column vector. When we vectorizing one of the rules of thumb that might help you navigate these, and is that while we have a different nodes in the layer, we'll stack them vertically, so that's why we have z11 and z14, and those correspond to 4 different nodes in a hidden layer. And so we stack these 4 numbers vertically to from the vector z1 to use one more piece of notation, these 4x3 matrices, and here which we obtain by stacking w11, w12, and so on. We're going to call these matrices W for all of these W's. And if I want to show you the matrices of that is like that. Here we can say it's W transpose W2 transpose W3 transpose W4 transpose, and there are multiply by x1, x2, and x3. Let me write again because we don't have any space in here. Right in here. It was our W weighted matrices. W superscript 1, subscript 1, but it's transpose. W superscript 1, subscript 2, transpose. W3 superscript 1, transpose, and W4. These are our weighted matrices, and if you multiply them by x1, x2, and x3 plus some biases that are B11, B21, B31, and B41. If we have 4 neurons for these, and all of them are Z for superscript 1, and it became like that. If we just use these matrices, you just imagine these are a matrix. This is our matrix. This is our answer, and we can and the answer is like this: Z11, Z21, Z31, and Z41. It's this matrix. The answer is like that. So just take these 4 values and stack them together in a vector called, we say them A, after activation function, and in this case we use just sigmoid. This is going to be a sigmoid of Z1, where this now has been implementation of the sigma function that take 4 element of Z and applies the sigmoid function element wise to it. So just recap, we figure it out. Z1 is equal to W1 times the vector x plus the vector b1, and the a1 is a sigmoid times of the z1. Let's just copy these of them, and what we see is that for the first layer in here, the neural network given the input x, we have, for this one, the z1 and is equal to w1 x times x and plus b1 and a1 is sigmoid of z1, and the dimension of these are 4 by 1 equals, this was a 4 by 3 matrices times a 3 by 1 in vector in second layer, and for the last one is a 4 by 1 vector b, and this is 4 by 1 in dimension for the last layers. So remember that we said x is equal to a0 because in here we say we numbering them by the 0 cases. So do you have question about them? Alright, so we continue that, and we show you some neural network representation learning. Just for the last output, just let me explain it to you. We want to say y hat is equal 2 of 2. If you want to, you can actually take this x and replace it with a0, since a0 is, if you want to, as an aliases of vector of input feature x. And now through a similar derivation you can figure it out that the representation for the next layer can also be written similarly where the output layer does it. So it has associated with it, and so the parameter w2 and b2, that means the weight, the second for the second input is 2 and the bias is 2 for the next neurons for the for this layer, and it goes on at to the end. So this is how we use for how we can write them. And if I want to a little bit show you like how to write it clearly, like some implementation, we can write like that. And for the next one we can say it's different. There are x, and for the next layer is not x, because in here we have inputs. The second one is the layers, there are a. For the next layer, because we have the last layer are inputs, but in this layer the last edge that they are fully connected is not the inputs. They're the neurons in the first hidden layer. So because of that we just write a1 for the I neurons. The I represent 1, 2, 3, I1, and these superscripts are for the number of the layer that we use. So this is a, this is x, because this input in, and this is for the last layer. And we use b2. Let me write, so clean one, z1i is w1 xi plus b1, and a1i is the activation function, which is sigmoid is z1i, and the z2i is w2a1i plus b2, and the a2i is the sigmoid of the z2i, and all of the i's are for I in 1, 2 m. Just a second. Okay, so this is became an, or maybe nx by m. We can use for matrices. I'm just going to give away that punch line and tell you what you need to implement in order to have vectorized implementation for this loop. Let me just zoom out them. It turns out what you need to do is compute it. The z1 is w1 multiply x plus b1, and a1 is sigmoid point of z1, and then z2 is w2 multiply a1 plus b2, and then a2 is sigmoid 1 of the z2. So if you watch the analogically is that we went from lowercase, that we can use vector xs to just use them, be stacking up them in different columns. If you do the same thing for these z's, so you take z1 and I and z1 and 2 and so on, and these are column vectors up to z1 and m for the last elements of the loop. So this is the first quantity, that's all m of them, and stack them in columns. Then just gives you the matrices z1, and similarly you took a look to say quantity and take a11 and a12 and so on to a1m. You stack them up in columns, and then it's just as we went from them for the z. This goes from to this go to which vectors. This use a1, and that's over there similarly for z2, and we use go them at the end for all of them. So if you just want to tell it again, it's the weight of the for edge of the each neuron and its input. We multiply them, and for partial sum of them we adding them, and at last we add just one bias for each neuron, and for all of them we just use activation functions. So at the end it doesn't matter its input layer or its hidden layer for the previous layer of that. For each neuron, for calculated them, if there are some nodes in previous layer, we just multiply them, the last answer of them, the input of these, we just multiply the output, the neuron of the last layer, by some weights, and sum all of them and plus them like one bias, and we held it to one activation function. I write f because always it's not a sigmoid one, and this is the output of this neuron. So if we have so many neurons, the output of this neuron is the input of the next one, like what we calculated for this. For the next computation, this is like the last layer input. We just told it to you. So the neural networks are just a simple partial multiplies and sum of them for the last layers. It's not so difficult to calculate them, and this is why we use neural networks. So for the last minutes, I just show you an example like and or, and I don't know we have any time to show you the XOR. If we can't show them, we will say it to next session. For and or, remember that we just use and or. We use first for AND gate. Look, we have x1 and x2 neuron. This is input. We have one neuron for this. It can be 1, 0 or 1, and it can be 0 or 1. Just for calculated the simple one, just give a randomized integer in that. Think that the weights are the half one 0.5. There are W's, and for simplicity you think just the bias are 0. We just remove them. It's not necessary we just have one answer. It can be in so many answers by changing the W's and activation function and the pair of the BIOS. So it's not necessary we have just one answer. We just want to find so many answers. We just find one answers in so many answers that we have. So for this one, if we use this, if x1 is 0 and x2 is 0, the equation is w x1 multiply w1 plus b plus x2 multiply w2 is x1. Imagine that both of them are 0. We just solve them by pair of x1 x2 0 0 0 1 1 0 1 1. The equation after this function sigmoid, we call them f, is for this equation, for this formula, the equation is 0 plus 0 plus 0. This is bias, this is y1 x1, and this is y2 x2, which is 0. For this f is 0 plus 1 plus 0, it's 1. For this 1 plus 0 plus 0 is equals to 1, and for this is 1 plus 1 plus 0, it becomes 2. So we have the z for them. For this is 0, this is 1, this is 1, this is 2. But we want to use a function that if we put z on that, the y hat, it became like act like AND gate. So how we can use sigmoid, or not sigmoid, we use, for sigmoid we use step activation function. If like we want to calculate it fz, we can use if z is bigger than number x, the answer was 1, and if the, let me write here, if z, have two cases, if z is bigger than x or it's less than x. In this case we want to output the answer 1, and this, in this one we use it 0. Oh, I'm sorry, there weight was, I forget that it's half 1, it's 1 for this case. I write it for half 1 for the OR gate. So in AND gate, all of the answer must 0 except the last one. So it's 0 1 1 1 and 2. So for just this one we must have y hat 1. For all of them we must have 0. So which x we can use it? We can use, for this x, we want to figure it out which x, which is the z in here is 2, is here is 1, is here is 1, and in here is 0. For which x the answer just be 1 for this input, and for which x the answer is 0. We can use for x equals to 2. If we x equals to the answer, the sum of these weighted by inputs and plus the biases, if the answer is less than that, we can say the answer is 0, and if it's equal or bigger than that, larger than that, we can use the answer is 1. So in this sample, if we think that the weight 1 is 1, this one is 1, and the bias is 0, then the activation function is like that. The x became 2. It's not x because you take a mistake with the x input. I use it like s. The s is equals to 2. So for the last part, I just solve the OR gate y hat for this must be 0 1 1 1. So the x1 w1 plus x2 w2 plus bias, and after that the z, we call them z, the activation function of z. Okay, just imagine that we have this neural network. There are x1 and x2, and we think w1 is half of the 1, 0.5, and the w2 is half of the 1 is 0.5. So in this case, and for simplicity, you just imagine that the b is 0. So for that is 0 plus 0 plus 0 equals to 0. For this is 0 plus x2 is 1 and w2 is 0.5, so it became 0.5 plus 0, it became 0.5. For this is x2 is 0 but x1 is 1 and w1 is 0.5 and w2 is 0.52, so it became 0.5 plus 0 plus 0, it became 0.5. For this is 0.5 plus 0.5 plus 0, it became 1. So these are our z's, but these are our answer, it must be y hat. So which activation function number we can use if the answer is larger with that threshold, we call them the answer is 1, and if they smaller that threshold, we call them the answer is 0. We can use s like that is 0.5. If the answer is equal or larger than half of the 1, we can say the answer is 1. So it became 1 1 1 and 0 if the sigmoid step number function is equal to 0.5. Yeah. So our times is over, and so guys, do you have any question for this? Oh, sorry, I didn't saw your comments. What is the final y hat? Y hat is the y hat is the z, the activation function of the z. If you you just find the correct step number activation function for that, the answer, the y hat, must be equal to activation function of the z. Okay guys, do you have another question? Okay guys, goodbye for next session. I will see you on next session.